Hello, everybody. I'm Alex Martinez, and I'll be giving a presentation on blade root design, the loading, and attachment methods. We'll start off by going over the importance of good blade root design and attachment. And from there, we'll talk about the different methods of attachment, as well as loading cases, and also a fatigue study before talking about the future of root design. So first, the importance. The obvious one is safety. Um, the root of the blade is where the blade itself connects to the hub. And obviously, if that is not well done, well engineered, then you can end up with blade throws, which is where the blade itself disconnects from the hub and gets tossed during operation. An example of this was in 2013 at the Ocotillo wind project in Southern California, where a blade got thrown. Thankfully, nobody got hurt, but it's still a scary sight to see, especially considering this can hurt wildlife as well as humans or just damage any infrastructure in the area. Another equally important reason is public opinion, right? Things are only as safe as people think they are. And a major force of pushback against the wind industry, wind power industry, is that people consider turbines to be unsafe. So by making sure that these connections are always nice and tight and secure and safe, hopefully people will start to see that wind turbines really aren't dangerous, and it's good to move in the direction of better sustainable energy. So what are some challenges with connecting the blade to the hub? Well, for one, you need strong enough connection, right? The connection strength has to be good enough such that you can take the blade loads and transfer from the blade through the root and the connections to the hub. However, that's challenging also because material properties are different. A steel-to-steel connection is very different strength-wise than just trying to bolt the hub itself to the blade itself to the steel hub. So we have to consider the fact that the composite blade definitely has different strengths and stiffnesses than the steel hub. And then lastly, cost. Of course, cost is a major factor whenever you're talking about designing anything, especially in the case of the root of the blade, where they say 20% of the total cost of the blade goes into making the root. So all the more important to get things done right, but still for cheap. So now what are the attachment methods? Well, here's 4 of them. These are the 4 that you'd find if you're looking for research online. These are the most common. Rather, some are more common than others, but these are what you will be finding. There's flange type, hub type, T-bolts, studs, and inserts. So those are all depicted here in this image to the right. Flange is on the far left, and then studs and inserts on the far right, and all in between. We'll talk about each one momentarily. So flanged root connection, this is based on the idea that the root of the blade it forms a composite flange, right? And there's a hole in this flange for which a bolt can pass through. However, we don't want the brunt of the load from the bolt to be going into the composite blade because it can destroy it and just tear through it. So what we do is we have a steel pressure ring that we use to sandwich the composite flange against the hub flange, and then we send a bolt through all 3 components. Now, an issue with this, though, is that there needs to be completely tight spacing between the composite blade flange and the steel pressure ring and hub flange. So filler material and windings are used to create that tight fit to ensure that the blade is not rocking around in its little sandwiched flange assembly. However, sometimes those windings and fittings do come loose, and this is a major source for fatigue failure because now we have this composite blade constantly rubbing up against steel and getting shredded away slowly. So this flange root design, it's simple, but it's very heavy. We have a steel plate resting on top of extra material with a flanged composite blade, right? And then also it has poor performance and fatigue for that rubbing reason that I just mentioned. For these reasons, this is more of an outdated method. We do not really see flange root getting implemented anymore. Next up, we have hub type, which is basically this tapered cylinder that's embedded in the root. While the blade is being made, you have this cylinder in there, and then the cylinder is going to get bolted directly to the hub when it comes time to assemble. However, this method is altogether not that great, especially for large scale applications. It does poorly in fatigue, and it's not very good at transferring the loads from the blade to the cylinder inside. Next up, we have T-bolts, which are the most common method that's used nowadays, and it involves holes drilled longitudinally and radially into the root. The radial holes house a cylindrical nut that is press fit into it, and then longitudinal holes is where you will put your threaded studs. And you'll thread these studs one end into the cylindrical nut and tighten it, pre-tension it nice and tight. And then the other end of the stud is going to be put through the flange of the hub, and it'll be bolted down to secure that the rest of the way. So now, some good things about T-bolts are that it's cheap and simple. Bolts and nuts, not very complicated. Been doing it forever when it comes to assembly of things. So it's not difficult to acquire the materials for this, and people generally understand what's going on with this attachment method. Additionally, it's very good in fatigue. However, it is kind of on the heavy end when you have these beefy steel bolts and steel cylindrical nuts as well. It can kind of weigh down the blade, and as you increase weight, right, it's more resistance, which is more losses in energy production. Next up, studs and inserts. So this one just has holes longitudinally, and in these holes, they can either be drilled or they can be left as like vacancies while you're laying out the composite layers of the blade during manufacturing. And in this method, you have these inserts that you will apply adhesive to the outside of, and also adhesive in the hole, and then you'll jam pack it tight into that hole. And then these inserts can be male or female, meaning they can have threaded studs pointing out, or they can just have threaded inserts for you to thread in your own stud as well. So this is great because it's lightweight and it's fantastic in fatigue. However, it is difficult to implement because one, you have to take this great care while you're laying out your blade while building it to leave room for these holes. Additionally, it's difficult to guarantee that the adhesive is applied evenly all around the insert, so that way the load transfer can work from the blade to the insert to the bolt and ultimately to the flange in the hub. And then also, since this is less traditional than just bolts and nuts, it's more expensive. So there's definitely pros and cons, but T-bolts are the way that the industry is currently assembling their roots and hubs. So now the connection process, there's basically two ways that the blade will get connected to the hub. It'll either get connected while the hub is on the ground, and then the entire hub fixture gets lifted up to the nacelle, or you can attach it to the hub while the hub is already in the air in the nacelle at the top of the tower. So I'm going to go ahead and show this video of the aerial attachment, and you guys can kind of see what's going on with that. There's no audio for this video because the music is just blaringly loud and doesn't really add anything. So here we can see the operator within the hub is, with the help of the crane, trying to pull in the root and line it up into the holes of the hub. And yes, kind of a scary job, but someone's got to do it, right? Yeah, as you can see, he's taking his time, but I guess you can't see, but you can see that he is pulling it in closer to the hub, so that way he can line up those holes and bolt the back end and get a tight mating of the T-bolts to the nuts on the back end in the hub. And yeah, you can see it's getting pulled in deeper. So now, as part of any good design, you have to understand what kind of loads you'll be seeing. So I found this loading study where they set out to model a blade that would have a blade length of 50 meters and fits into a 3 megawatt wind turbine that would be experiencing 12.3 meters per second of wind speed. So for this model, they used a mathematical model based on blade element momentum theorem, which is kind of cool because we learned about that. And what they were able to do is see how different factors affected the loads that the hub bearing and ultimately the bolts that connect to the hub would experience during operation. So one thing to note is that this study is solving for what they call the equivalent load at the bearing. That's this L sub B BL, and this force is opposing the radial force of the blade being pushed into the hub or out of the hub by both centrifugal forces as well as gravitational forces. And then this load is also opposing any moments generated by thrust and causing flapwise moments in the blade during operation. So what was found was that errors in pitch and yaw did not have a huge impact on the root load, neither did small altered amounts of turbulence. However, cone and tilt angles did have a large effect on this equivalent load. So I have this image here to help you visually see what the cone and tilt angles are. The tilt angle is the angle that the nose of your hub points in relation to the angle that the wind enters. And then the cone angle is how far forward your blades are pointed with respect to the plane of rotation. Okay, so now the results that they found are pictured in these two graphs below, or I guess right there in front of you. And we can see that the magnitudes we're talking about are in the meganewtons range. So with no tilt or cone angle, 4 meganewtons max. With the tilt and cone angle, you're looking at around 6.1 meganewtons. So these are pretty substantial loads. Another thing that I think is worth pointing out here is that for the cone and tilt angle 0 case, we see a pretty expected distribution of loading. On the x-axis here, we have angular position as the blade makes its way around one rotation around the hub. And as you'd expect, we see kind of a symmetric increasing and decreasing of loading as we pass important parts of our rotation cycle. However, with the cone and tilt angle, it gets a little bit wonkier and also leads to overall just higher loading. So then, right, we were talking about 6.1 meganewtons max if you have that cone and tilt angle. Is that doable with bolts? Well, some common fasteners used for 3 megawatt turbines for this root joining application is M36 T-bolts. And these have a minimum diameter of 28 millimeters and a minimum yield strength of 940 megapascals. So doing a little bit of quick math, some stress is equal to force over area. We can find that the yield force for these bolts would be about 0.58 meganewtons, which would mean technically with no safety factor, we could do this with around 11 bolts. I don't think 11 bolts is a good move, but technically that's what it would be. So let's talk about why we might want more than 11 bolts, even though technically we could handle it. Of course, you guys are familiar with safety factor, but just to really hit it home, redundancy is very important. We don't want to have it that if one bolt fails, the entire thing falls apart, which is why we have plenty of bolts. One, it keeps the loads lower per bolt, but also it just helps in case one bolt does fail, there's others to pick up the slack. Additionally, as I mentioned before, the material difference between steel hub and composite blade makes loading kind of difficult, right? Although these 11 bolts could handle all of the load, it would create stress concentrations in the blade itself, in the composite blade, and likely would just rip right through the blade, still leading to ultimate failure or catastrophic failure of a blade throw. So we need to keep the bolt loads low enough that we don't create stress concentrations in the blade itself and rip through it. And then also fatigue. Although we could handle max yield strength, you don't want to because you can't handle it at all times for hundreds of thousands to millions of cycles. So fatigue, of course, is another big factor to think about when considering the safety and implementation of all these bolts. Also, I could not find a definitive number for this is how many bolts for this sized root radius. However, what I was finding is generally these bolts seem to be spaced out around 5 degrees all the way around the circumference of the root, and you see numbers typically 64 to 72 for like these 3 megawatt applications. So next, I found some fatigue study that I'd like to talk about. So this fatigue study was performed on a 54-meter long blade that weighed 14.5 tons and was part of another 3 megawatt turbine. So the way that this study was performed was there was a physical test that occurred, and then a mathematical model and FEA model to try and understand why it fails in fatigue, even though traditional models do not predict it. And pictured here is just the setup showing the T-bolts and also what kind of stresses can be expected as this test occurs. So the type of test that is used is called dual axis resonance testing, and that involves moving the blade both in the flapwise and edgewise directions at the same time. In the edgewise direction, we did 700,000 cycles with a mean moment of 0, but a amplitude moment of 4.5 meganewton meters. And then flapwise, 500K cycles, mean moment of about 6 meganewton meters and amplitude moment of 5.3 meganewton meters. So here I have a quick little video to show you of what the testing would look like, just that way you can see what it means to really be moving both flapwise and edgewise at the same time during testing. So as you can see, a lot of movement going on with the blade. However, this is a good representation of what the blade would experience during its life, if not an overestimate of loading. So it is a good way of testing for fatigue. So then what ended up happening? Well, from the physical test, several bolts failed. However, there was not catastrophic failure with the blade throw. However, these bolts were elongated, some of them bent, unable to carry the loads, but still the connection was tight enough to keep the blade attached. There's just some joint separation at certain locations. So the traditional way of identifying what loads are expected at these bolts is with the basic cantilevered cylinder kind of model. However, that model does not predict the failure that was shown from the physical fatigue test. So that's what this study was about, was to set out why does this model not line up and what is actually happening. So an FEA model was created using shell type elements. And from that, it was found that this effect of bumping occurs, as the research paper called it. So during bumping, parts of the cross section of the root are getting elongated and stretched out, and some parts are getting pushed in, giving this weird circular shape shown in the bottom right. And the parts that are getting pulled out from the circle are experiencing less load than the cylindrical model projects. And then those that are getting pushed in are experiencing much greater loads than the cantilevered cylinder model expects. And that is what leads to the failing of these bolts that ended up being seen in the physical test. And the big takeaway of this is just that now this bumping does need to be in the forefront of designers' minds when considering the loads that are going on here. There is deformation, which changes the loading, and it's important that designers realize that when trying to create the best connection between the root and the hub. So what comes next? Well, as I mentioned before, studs and inserts are great for fatigue. They're great because they're lightweight. Their biggest problem is that they're kind of expensive and difficult to implement. But over time, right, as technology becomes less new and more people are used to using it, the price of implementing it goes down. And as the cost goes down, this could be a very, very valid replacement for the T-bolts that are so popular today. So pictured here in this slide, I have a patent in the bottom left here showing a new design for an insert, and then on the right is a projected path for a new wind company talking about revolutionizing the way that roots and hubs are connected. So then, with all that said, here's a picture of my works cited, and I'm ready to field any questions you guys might have for me. Thank you for listening.